Hi Bobcats! This video is the first of two in which we'll look at example problems of the types that you'll be looking at on a quiz or a test. Our objectives are to predict the concentration and time values of reactions with integrated rate laws, to graph data to identify the order of a reaction, and then to use these terms correctly. In this example, we are given data for a chemical reaction for the isomerization of CH3and and if you look at this data table, notice that it's quite a bit different than the method of initial rates data. We are given two columns of data. The first column is time, not the experiment number, but time, and the second column is pressure. Now, you can derive an expression using the ideal gas law that tells you that pressure is directly proportional to molarity. So usually when we're working with gases, it's easier to measure the pressure of the gases. And so we just use pressure in all of these expressions the way we would use molarity for a solution. The ideal gas law can give you that conversion factor if you need it, but the math works out to be the same if you do it all in terms of pressures. So that's what we usually do. And it's not labeled here on the data table, but the pressure for this problem is given in torr. All right, so what are we going to do here? Well, since we're given time and pressure data, which is equivalent to concentration data, we need to make three graphs of the data. And from that data, from those graphs, determine what the order of the reaction is, and then the slope of the most linear plot will tell us what K is. We also have this beaker icon in the upper right to remind me to tell you that if you are in the CHEM 1142 lab, you'll be doing an experiment with crystal violet that uses the integrated rate law approach. So here's how I started the data analysis. I am using the graphing tool that is given in your textbook. It is figure 14.12. So this is in the integrated rate law section of the textbook down towards the bottom. Just keep scrolling down till you hit figure 14.12. And what I did was from the data table on the previous page, I typed in time and I typed in concentration. The computer then calculated for me the natural log of the concentration and the reciprocal of the concentration. So in order to get this natural log data, for instance, that very first natural log, all the computer did, let's see, I'm going to write this in down at the bottom, the computer took the natural log of 502. Right, so that natural log of 502 is what's in that square. So 502 is the concentration, you take the natural log of it, you get 6.218. For that last column, the computer took 1 divided by 502. And so that's where that last data point came from. All right, so over here on the right-hand side of your screen, the computer did the graph for us. The graph that we are seeing is the one that's boxed up here, selected. It's the concentration versus time. So our vertical axis is concentration, and our horizontal axis is time. The computer also calculated the equation for a line of best fit, y equals mx plus b. So y, in this case, is the concentration of A, and x is t. If this turns out to be our most linear plot, then k will be given by the absolute value of the slope. So if that's the case, k will be 0.03015. All right, well, let's look at the other plots because the computer has already calculated the natural log data and the reciprocal data. So let's pull up those plots and see what they look like. When you're using the tool in this section, you can just click on this tab up top that says natural log of A versus T. I'll have to advance to the next slide to show you. All right, on this slide, we are looking at the log plot. So notice we've selected the natural log of A versus T. So it is plotting T on the horizontal axis and the natural log data on the vertical axis. Notice how all of those data points just very nicely fall along that line. And we have an equation down below in the form of y equals mx plus b. So y represents the natural log of the concentration, and x represents time. If this is the most linear plot, then the slope will be the slope will give us k once we take the absolute value of the slope, and so k will be 2.0775 times 10 to the minus 4. Now let's take a look at the last plot, the reciprocal plot. All right, on this slide we have that final plot, the reciprocal plot. So the reciprocal plot was chosen on the tool. It is graphing this data on the y-axis and it's graphing time on the horizontal axis. Notice that the calculated line of best fit doesn't quite line up with the data points very well, but if this one works out to be our most linear plot, then y is equivalent to 1 over the concentration, x is equivalent to t, and we will get the value of k by taking the absolute value of the slope. Now, let's take a look at all three of these plots together so it's easier to compare them. All right, this slide just shows you the three plots from the last three slides all together on one plot so that you can visually compare them. I think it's clear that the middle plot is the most linear, meaning that the data points fall closest to the line of best fit for the data. If that was not really obvious by looking, because sometimes with real kinetics data it's not this obvious, we would need to fall down here to the correlation coefficients. So this R squared value is the square of the correlation coefficient. If something is absolutely perfectly linear, so every data point absolutely falls along that line of best fit, the R squared value will be 1. If the data don't quite fall along the line, R squared will have smaller values. And so it's obvious from looking at these R squared values that that center point is the most linear, because R squared equals 1 means that this is perfectly linear data. All right, so that tells us that this natural log plot is our most linear one. If the natural log plot is the most linear one, then it's going to be a first order reaction. Now, if instead the concentration plot, which is the one on the left, had been most linear, then it would be 0 order. And if instead the reciprocal plot, or the one on the right, had been most linear, then it would be a second order. But the scenario we have here is that it is a first order reaction. And we can read the value of k by taking the absolute value of the slope. And so the slope is the number that's in front of x. And so k for this reaction will be 2.0775 times 10 to the negative 4.